Chapter 2, Accelerated Motion. In this chapter, we will learn about acceleration, interpreting velocity time graphs, using the four equations of motion, also called the SUVAT equations, SUVAT equations, describing a method for determining the acceleration due to gravity. That is, we will learn how to find g by experiment. Explain projectile motion in terms of horizontal and vertical components of motion. We will resolve the velocity in the horizontal direction and in the vertical direction. Now, once we complete this chapter, you should be able to do these things. That's why they are called learning outcomes. And even in the O-level class, you would have learned about acceleration. Acceleration is change in velocity over time taken. Then you have learned that the gradient of a velocity time graph is the acceleration, and the area under a velocity time graph is the displacement. That is the area between the line and the x-axis. That is the displacement. Then over here you will learn 4 equations. Those students who are doing M1 will learn 5 equations. I will briefly show them to you so that you have a good idea of what you need to know. It's given over here. So these 4 equations are extremely important. V, U, A, T and S are the 5 quantities that you have in these equations. V is final velocity, U is initial velocity, A is the acceleration, T is the time and S is the displacement. Alright. Okay. So and these equations are applicable only when the acceleration is uniform. If the acceleration is changing, you can't use these equations. Now, if they have not said that the acceleration is uniform, you have to assume that the acceleration is uniform and do it using those equations. Now, even if they say the velocity is, even if they don't say the velocity is constant in a certain question, you have to assume that the velocity is constant and do the question. Okay, describe a method for determining the acceleration. So we will see that we will also use one of these equations to calculate the acceleration of free fall. This g is also called the gravitational field strength. Okay, and then we will learn how to resolve this. So we use v cosine theta and v sine theta to resolve in the vertical and horizontal directions, also called the y-axis direction and the x-axis directions. Okay, let's see what the subtopics are. You have the meaning of acceleration, calculating acceleration, so using the equation. Now, if you remember, one of the equations here was the equation of acceleration. You can see here this first equation is an equation. If you rearrange, if you make A the subject of the equation, you get the equation for the definition of acceleration. Let's say you make A the subject here, then A is equal to V minus U over T. The change in velocity over the time is the acceleration. Okay, then we'll go back to this what we were doing. Alright, so over here you will learn deducing displacement, deducing acceleration. I told you the gradient and the area under the curve will give you the acceleration and the displacement respectively of from a velocity time graph. And then determining velocity and acceleration in the equations of motion, deriving the equations of motion. Now you should know how to derive those 4 equations. Uniform and non-uniform acceleration. I told you those 4 equations can be used when the acceleration is uniform. If the acceleration is non-uniform, meaning if the acceleration is changing, you can't use those equations. Now, the words that we use for uniform means constant, steady, not changing, remaining the same. All these mean the same thing. So they can give you different words for constant, uniform, not changing, steady, all mean the same thing. Okay, then acceleration caused by gravity is the gravitational field strength or acceleration of free fall. Determining that motion in 2 dimensions. If you do higher levels of physics, you will have motion in 3 dimensions also, but we are not concerned about that. We want motion in 2 dimensions. That's why we resolve the velocity in the horizontal and vertical directions and do it, because it is in 2 dimensions. Now, for example, if something is moving along a certain axis, that means it is moving in one dimension. If it's moving in a straight line, that is one dimension. If it's moving in the x and y axis, that region, okay, that surface, then it is moving in two dimensions. For example, if something is let's say on a flat floor, and if it is moving in different directions on the floor, it is moving in two dimensions. Okay, if it's moving along a line, it is moving in one dimension. And three dimensions is if it is moving in the x, y, z axis direction. Okay, so it is let's say something is moving in the air. If it's moving in the air, it can move left, right, up, down. So it is moving in three dimensions. So let's apply this for a vehicle. For example, a train. A train moving in a straight line is moving only in one dimension. For example, let's say the railway tracks are straight, then the train is moving in one dimension along the railway track. Two dimensions, cars. Okay, the vehicles, the land vehicles we use move in two dimensions, because in a car we can turn left, right, and move also forwards, backwards. But a train can only move forwards and backwards. Okay, so the train moves in one dimension, cars move in two dimensions, and helicopters can move in three dimensions, because in addition to moving forwards, backwards, and sideways, the helicopter can also move up and down. So now you understand what is one dimension, two dimensions, and three dimensions. Okay, then a projectile. A projectile is an object that is thrown in the air. For example, if you take a stone and throw it in the air, that is, it becomes a projectile. Same thing with a certain object like a ball. If you throw a ball in the air, that ball is now a projectile. And there are certain words you have to know when we are doing questions on projectiles. The path of a projectile is a trajectory. Trajectory. The path a projectile takes is a trajectory, and the shape of the trajectory is a parabola. In other words, it's a parabolic path. Okay, for mathematics you would have learned the parabola shape, so we will see that over here also. Then the horizontal distance that a projectile travels is called the range. Let's say you throw a projectile from the ground at an angle, then it will land somewhere. So the horizontal distance that it traveled is the range, and the time it was in the air is called the time of flight. Okay, so trajectory, range, and time of flight. And finally we have the summary. Let's go through the summary also, so that you have a better understanding of what topics you will be covering in this chapter. Acceleration is equal to the rate of change of velocity. This is the definition. In paper 2, they can ask you to state the definitions. That's why I have said several times, whatever is in the green boxes in this book is very important. Now you saw that these equations were earlier given in the green boxes. It was highlighted in green. Whatever in your book that is highlighted in green is extremely important, because they can ask you to define that quantity or that term in paper 2, and in A2 you will have to do that for paper 4. Okay, so acceleration is equal to rate of change of velocity. Acceleration is a vector quantity. You have learned this in the O-level classes also. The gradient of a velocity time graph is equal to acceleration. The area under a velocity time graph is equal to displacement or distance traveled. I mentioned this earlier, and you have also learned it in the O-level or IGCSE 9-1 classes. The equation of motion for constant acceleration in a straight line. You see the word over here, constant acceleration. Only we can use this equation. And you can also see here straight line, because if the direction is changing, even if the velocity, even if the speed is constant, the velocity will change, because velocity is a vector quantity. So if the velocity is changing, then the acceleration is not constant. Okay, so an object, for example, moving in a circular path with a constant speed has a changing velocity, even though the magnitude of velocity, which is speed, is constant, because the direction is always changing. We have learned this, you will learn this under circular motion. Okay, so let's say something is moving at a constant speed of 5 meters per second, but if it is moving in a circle, the direction is always changing. Therefore the velocity is changing. Speed is a scalar quantity, velocity is a vector quantity. So for velocity to be constant, both the direction and the magnitude has to be the same. Magnitude of velocity is speed. So speed is constant, but because the direction is changing, the velocity is changing. So if there is a change in velocity, the acceleration is changing. And we can't use these equations because these equations can be used when the acceleration is steady or constant or uniform, in other words. Okay, then vectors such as forces can be resolved into components. Components at right angles to one another can be treated independently of one another. For a velocity v at an angle theta to the x direction, the components are this. So we get this using trigonometry. Okay, if you draw a triangle and if you draw a right angle triangle and if you label angle theta, and let's say you know the hypotenuse of the triangle, then you can find the other sides by using trigonometry, cosine and sine. We will see the details afterwards. Then finally, for projectiles, the horizontal and vertical components of velocity can be treated independently. In the absence of air resistance, the horizontal component of velocity is constant, while the vertical component of velocity increases downwards at a rate of 9.81 meters per second squared. This is the acceleration of free fall. We will again go into the details. Now remember, this is the summary, so you may not understand everything over here 100% because we have not covered the theory part yet, but I went through this so that you can have an idea of what content is important and what content will be covered. Now this last part, now if you throw a projectile, if there is no air resistance and if there is a projectile, that is an object moving in the air, the acceleration is vertically downwards, and the acceleration is the acceleration of free fall, which is 9.81 meters per second squared. In the O-level classes or IGCSE 9-1 classes, you would have used 10 meters per second squared, but in this A-level class we are using 9.81 because that 8 is that 10 is an approximated value. Okay, so for an object that is in the air, when there is no air resistance, the only force acting on it is its weight, and according to Newton's second law, the resultant force and the acceleration are in the same direction. Always the resultant force and the acceleration are in the same direction, and it is the resultant force which produces the acceleration. So if the resultant force is down, which is the weight, or the only force is the weight, so the resultant force is the weight, this produces an acceleration, and the acceleration due to the weight is this. Okay, we call it the acceleration of free fall, the acceleration due to the gravitational force. Gravitational force is also called weight. Okay, let's go to the beginning of the chapter now. You have an idea of what content is covered in the chapter. Okay, now this creature is the fastest land animal. It can reach maximum speeds of 108 kilometers per hour in a few seconds, in just 3 or 4 strides, taking only 2 seconds. But the cheetah cannot maintain this speed for a long time. Okay. Then here we have some examples of what forces can do. Okay, now let's go through this bit also. Examples of objects accelerating. Whenever there is a resultant force, there is an acceleration. Now this resultant force causes the acceleration, not the other way around. Sometimes students confuse. They think the resultant force is due to the acceleration, which is incorrect. It is the acceleration, sorry, it is the resultant force which produces the acceleration. So you have the formula, Newton's second law, F equals ma. That F is a resultant force. It is this resultant force which produces the acceleration. Okay, so let's look at some examples over here of what forces can do. Whenever there is a resultant force, there is an acceleration. A car speeds up as it leaves the town. The driver presses on the accelerator pedal to increase the car's velocity. So a resultant force can cause an acceleration. Acceleration is an increase in speed. For example, over here, the car is accelerating. Then over here, a car setting off from the traffic lights, there is an instant when the car is both stationary and accelerating. Now if there is an object that is stationary, it can also be accelerating. Again, this is something that students don't understand properly. Let's say you throw something up. Okay, when you throw something up and at the highest point, okay, so here we have again an example of a projectile. When you throw something up, what will happen is it will reach the highest point, and at its highest point the vertical velocity is 0. Okay, so when you throw something up, when it reaches its highest point, let's say you throw something up vertically, no sideway movement, then what will happen is at the highest point the velocity is 0, then only it comes back down. Now even though the velocity is 0 at the highest point, there is still an acceleration at the highest point, and that acceleration is 9.81 meters per second square. That is, so throughout the motion of the projectile, when it is going up and coming down, the acceleration is vertically downwards 9.81 meters per second squared, even at the highest point where it is stationary. Okay, so similarly, that's what they say over here. A car setting off from the traffic lights, there is an instant when the car is both stationary and accelerating. Otherwise, it would not start moving. A car traveling around a bend at a steady speed. The car speed is constant, but its velocity is changing as it changes direction. Now, this is an example of circular motion. You see, the car speed is constant, but because the direction is changing, the velocity is changing. Okay, so resultant force can cause a stopped object to move. It can cause a change in direction of a moving object. Then also it can cause a moving object to stop. It can cause a change in the shape of an object. And over here we can see the change in direction. The speed also changes, the direction also changes. And you can see over here, this last one, the gravitational force, which is the resultant force, makes the stone accelerate when the stone is dropped. Alright, so over here they explain what acceleration is. Anything that speeds up is accelerating. But if we have a negative acceleration, that is called a deceleration. Deceleration is when the object is slowing down. Another word for deceleration is retardation. Okay, so you can say a negative acceleration is a deceleration, also called a retardation. Yeah. And this is the equation for acceleration, and also it is the definition for acceleration. Now you can see over here, this is in the green box. Also we can say it is highlighted in green. If it is highlighted in green, that means it's a very important equation, very important definition. You have to memorize it with understanding, because in paper 2 they can ask you to write this down. So here is the definition of acceleration. Acceleration is rate of change of velocity, and if you write it as an equation, average acceleration is change in velocity divided by time taken. And here it is in symbols. Change in velocity means final velocity minus initial velocity. We use simple v for initial velocity, and we use we use simple v for final velocity and simple u for initial velocity. So u is initial velocity, v is final velocity. So we can write this as a equals v minus u over t. And you can see that over here. Acceleration is change in velocity over time. Okay, so you can see the sprinter has a greater acceleration than the car, but her top speed is less. So in the beginning she accelerates faster than the car, but eventually the car overtakes her because the car has a greater top speed. The SI unit of acceleration is meters per second square. The SI unit of speed is meters per second. The SI unit of time is seconds. So the SI unit of acceleration is meters per second squared. By the way, whatever is in your book that is in green bold letters is also very important. For example, you see here, this word is in green bold letters. That means you have to know the meaning of it. The meanings of these words are also given in the glossary. So it will be given somewhere here, and also it will be given in the glossary. You can go to the glossary, go through the meaning of the word. For example, if it's here, it's acceleration, then also you can go through this acceleration definition. Then you can put everything together. So whatever points that are missing here, which is in the glossary, you can write it down. Or whatever points that are missing in the glossary, which is over here in the chapter, you can write it down. And you can have a more complete definition of what acceleration is, or whatever the meaning of that term is. Okay, to help you understand better, let's go through this example for consolidation. Leaving a bus stop, a bus reaches a velocity of 8.0 meters per second. After 10 seconds, calculate the acceleration of the bus. A very simple question. First thing you can do is, if you want, you can draw a diagram and write down the quantities they have given in the question, because this will make it easier for you to do this question. It makes it less complicated. The initial velocity is 8 meters per the initial velocity is 0, because the bus is leaving the bus stop. So u is equal to 0. Okay, so you can write simple u equals 0. Then the final velocity is 8 meters per second. So you can write v equals 8.0 meters per second. And the time for this change in velocity is 10 seconds. So t is equal to 10 seconds. We are supposed to use the equation over here to find the acceleration. Now once you write the quantities, it will be easier for you to figure out which equation you are supposed to use. This is the equation that has v, u, t and the a. A is what you need to find. So that's why I said it's better to write the quantities given in the question, so that it will make it less complicated. It will make it easier for you to understand and solve the question. Because here, once you write it down, you see, okay, this is the equation that you have to use. Okay, then we substitute into that equation. V minus u is the change in velocity, that is final velocity, minus initial velocity, which is 8 minus 0, that is 8. And the time is 10. So very easy. Substitute and you will get 0.8 meters per second squared. 0.80 meters per second squared. Again, you can see they have given this to two significant figures. This is the first significant figure, this is the second significant figure, because here two significant figures, here two. So that's why we write the answer to two significant figures. Again, if you are not familiar with the rules of significant figures, I have uploaded a video, 2 videos explaining almost everything you need to know about significant figures. Watch those 2 videos. After that, any question you have about significant figures will be answered. Okay, so make sure you go through those, because it is not only used in physics, even in other subjects. Students, I have noticed, losing marks because they don't know how to do the operations with significant figures. Some of them even can't identify the number of significant figures in a number. Okay, so watch those 2 videos, then you will have a good understanding of how to identify the number of significant figures in a number, and also the rules of significant figure operations when it comes to multiplication, division, addition, subtraction, and all of those together. Example number 2. A sprinter starting from rest has an acceleration of 5.0 meters per second squared during the first 2 seconds of a race. Calculate her velocity after 2 seconds. They have given the time for the acceleration, so you can write down the quantities that are given. A is equal to 5 meters per second squared, t is equal to 2.0, and what do we mean by starting from rest is initial velocity is 0. Now when we use the word at rest, means the velocity is 0. At rest, stationary, not moving, all of them mean the same thing. That means the velocity is 0. At rest, not moving, stationary, all mean the same thing. The speed is 0. Okay, so we know that we are supposed to find v. U we know, a we know, t we know, and we are supposed to find v. Okay, so if you rearrange this equation to make v the subject of the equation, because we are going to find v, then you will get this. Substitute into this and you will get the final velocity v. A train slows down, example 3, a train slows down from 60 meters per second to 20 meters per second. Now this is the initial velocity v, this is the final velocity, sorry, initial velocity u, this is the final velocity v, and here is the time in 50 seconds. You are supposed to find the magnitude of deceleration. Acceleration negative means it's a deceleration, and deceleration is always a positive number. Deceleration cannot be negative. Deceleration is always given as a positive number. Once you do the question and if you get a negative value for acceleration, that means it's a deceleration or retardation, meaning it's slowing down. Okay, so finally you can write a statement with the magnitude of acceleration, which is the deceleration. Okay, so we'll do that now. Okay, so you write the quantities that are given, and also you can write the quantity you are supposed to find. Okay, so A equals question mark, but it is not just the A, they are asking the deceleration. Okay, so based on what you have written here, you know which equation you are supposed to use. You know V, you know U, you know T also. V is 60, U is 20, sorry, V is 20, this is the initial velocity, so this is U is 60, V is 20, and the time for that change in velocity is 50 seconds. Okay, then you are supposed to find the acceleration. Now you substitute that into this equation, you will get a negative answer. Remember, the unit of acceleration is meters per second squared. This means that the object is slowing down. Can you see over here, the final velocity V is less than the initial velocity. That's what makes this negative, because the speed is decreasing. The minus sign or negative acceleration indicates that the train is slowing down. It is decelerating. The magnitude of the deceleration is 0.80 meters per second squared. You see here, this number is positive because deceleration is given as a positive number. And how we identify whether it's a deceleration is if the object is slowing down. If it is slowing down, we will get a negative value for acceleration, which indicates it's a deceleration. Another name for deceleration is retardation. Okay, then the next one is about deducing acceleration. It is very important that you are able to understand these graphs or interpret these graphs. Previously, in the last chapter, we saw displacement time graphs, and I told you when the velocity in that graph is negative and when the velocity in that graph is decreasing. The gradient of a displacement time graph gives you the velocity. So if you have a negative gradient, that means the velocity is negative. It's moving in the opposite direction. If the gradient is decreasing, that means the velocity is decreasing. Don't confuse negative velocity with decreasing velocity. This is something students confuse. Similarly, over here, the gradient of a velocity time graph gives you the acceleration. Don't confuse negative acceleration with decreasing acceleration. Negative acceleration means deceleration. Decreasing acceleration means the size of the acceleration is decreasing. For example, if the acceleration is 12 meters per second square, it can reduce to 10 meters per second square, 5 meters per second square, 3 meters per second square. That is a decreasing acceleration. Okay, so the object is still increasing its speed but at a lower rate. Okay, so if you have a decreasing acceleration, the speed of the object is still increasing but at a decreasing rate. It's not increasing as rapidly as it did in the past few seconds. Okay, so we will learn that in detail when we are going through the graphs. Okay, when you see the graphs, you will understand it better. What you have to know is the gradient of a velocity time graph is numerically equal to the acceleration. The area under the velocity time graph, the area under means the area between the line and the x-axis. Now the line can even be on this side. Then it is not the area under the graph, it is the area above the line and between the x-axis. So remember, it's always, the displacement is always the area between the line and the x-axis or time axis in this case. And if the line is on this side, then you will get a negative value for the displacement. Okay, that means it has moved to the other direction from its starting point. So let's say we start calculating the displacement from a certain point. If it moves to the right of that point, by standard we take it as positive. Whatever is to the right or whatever is in the vertical direction, by standard we take it as positive. So if we get a negative value for displacement, that means that object is moving to the left or down, vertically downwards below its starting point. All right, so let's go through these graphs. Here we have a straight line. The gradient of a straight line is constant. That means the acceleration is constant. The gradient of a velocity time graph is the acceleration. So if the gradient is constant, if it's a line, the gradient is constant. That means the acceleration is constant. Over here, we have a velocity time graph. See, this acceleration, this gradient is greater than this gradient. The gradient of this line is greater than the gradient of this line. That means here the acceleration is greater than the acceleration over here. Then over here you can see the gradient is 0. The slope, another word for gradient is slope. Slope is 0. That means the acceleration is 0 because the gradient is 0. Okay, you can see, you know how to find the gradient, right? y2 minus y1 divided by x2 minus x1. Now over here the y coordinates are the same. If you take a point here and a point here, the y coordinates here and here are the same. So in the numerator it will become 0 when you do the calculation for gradient. So here the gradient is 0. Also you can think of the slope. See, the slope is 0. It's flat. It's a flat horizontal line. Slope is 0. That means acceleration is 0. So if acceleration is 0, there is no increase or decrease in the velocity, because if there is acceleration, the object will either speed up or slow down. If the acceleration is 0, then it means the velocity is constant. That's what you see over here. See, the velocity is remaining the same value when the time is passing. And these last two graphs are the two graphs that students confuse. That's why I told you, don't confuse negative acceleration with decreasing acceleration. Over here you can see the gradient is negative. Okay, if you do y2 minus y1 over x2 minus x1, you can see the first value is greater than the second value. Same thing, but here it's the other way. So this will give a negative gradient. If the line is sloping this way, it's a positive gradient. If the line is horizontal, the gradient is 0. If the line is sloping downwards like this, the gradient of that line will be negative. Okay, so we have a negative gradient here, and also you can see it's a line, it's not a curve. That means the gradient is negative and constant. The acceleration is constant and negative. Okay, so if we take by standard acceleration is positive to the right, in this case the acceleration of the object is to the left. Okay, the resultant force is to the left, but the object is moving to the right. If the resultant force is opposite to the direction of motion, an object will decelerate. If the resultant force is in the same direction of motion of the object will accelerate. And by Newton's second law, the resultant force and the acceleration are in the same direction. Okay, over here you can see it's curving this way, curving down like this. And the way you find the gradient of a curve is by drawing a tangent to the curve at a particular point to find the gradient of the curve at that point. So if you draw a tangent here, if you draw a tangent here, if you draw a tangent here, what you can see is the gradients of those tangents are decreasing when you move from left to right. And over here, if you draw a tangent over here at this point, it will be horizontal. So the gradient of the tangent is 0 here. Here the gradient of the tangent is positive. It becomes less and less and less positive, and finally it becomes 0. So what we can say is the acceleration is decreasing and it becomes 0. There is an acceleration, there is a positive acceleration, because the gradient of that tangent you draw are positive. So we have a increasing speed. If the acceleration is positive, what that means is the object speed is increasing. You can see that over here. You see, with time the velocity is increasing. Because if there is a positive acceleration means the speed increases. Positive acceleration means speed increases. Negative acceleration means speed decreases. So here the gradient is positive, and that means the acceleration but the acceleration is decreasing. If there is acceleration, the velocity should increase. So make sure you understand this. Over here the acceleration is decreasing, but the velocity is increasing, because there is acceleration, there is a positive acceleration. Okay, then over here what we can see is the acceleration is negative because the gradient is negative. So if acceleration is negative, that means it's a deceleration. The object should slow down, and that's what you can see over here. See, with time the velocity decreases. Okay, Here the acceleration is constant and it's negative, but here the acceleration is not constant, it is decreasing and but positive. Okay, so make sure you don't confuse these two. Alright, now over here in this graph, from here to here the acceleration is constant. After that what happens? The acceleration decreases and becomes 0. You have to look at the gradient of the graph. Let's find what the constant acceleration is. You can find the gradient of this line, or you can also use the formula. Acceleration is change in velocity over time. Now here there is a mistake. It's not change in displacement, it should be change in velocity. It's a mistake in the book. You can change it using a pencil. Change it to change the word displacement to velocity. Okay, and you have also learned that this equation can be used only when the acceleration is constant. And here we can see from 0 to 5 seconds the acceleration is constant. Therefore, the final velocity here is v, that is 20. The initial velocity is 0 and the time taken for that is 5. So 20 divided by 5, 4 meters per second square is the acceleration. Okay, now you can also find the gradient. It will also give you the same answer, 4 meters per second square. Okay, then about deducing displacement, I mentioned earlier the displacement is the area under the line, or we can also say the area between the line and the x-axis, because if the line is in the negative y-axis and the positive x-axis direction, then you will get a negative area. That will be above the line. Okay, so it has to be between the line and the x-axis. Okay, so what we can do is let's go through this example over here. First thing you have to do is, when you get a graph, look at what the axes are. Here the axis is velocity, here the axis is time. So it's a velocity versus time graph. When it's a velocity versus time graph, there are two things you learned. The gradient is the acceleration, the area of the between the line and the x-axis is the displacement. So those two things should come into your mind as soon as you see a velocity time graph. Okay, let's find the displacement in the first 15 seconds. Here it is a regular shape. So what you can do is you can find the area of this rectangle. It's a rectangle, the regular shape. So that is 20 into 15, which is 300. Okay, the displacement in the first 15 seconds is 300 meters. And over here, now here the object is moving with a constant velocity. Here the object is having a constant acceleration. So it doesn't matter whether the acceleration was 0, constant, changing. All you need to do is, if it's a velocity time graph, find the area between that curve or line and the x-axis to give you the displacement. So it can be applied even when the velocity or acceleration is changing. Over here the velocity is changing but the acceleration is constant. So what we have to do is, if you want to find the displacement in the first 5 seconds, you have to find the area between this line and this x-axis for the first 5 seconds. You can see it is a regular shape or a triangle. Okay, so what you do, use the formula for area of a triangle: half into base into height, half into 5 into 10, which is 25. Okay, the area is 25 and the unit is meters. Yeah, so that is the calculation over here, and this is what they are explaining. Displacement is area under velocity time graph. Okay, then about measuring velocity and acceleration. Okay, so here are the methods that we can use to find the acceleration. So one method is, now earlier in the previous chapter we learned how to measure speeds. There was 4 methods that we learned. There were 4 methods that we learned: using 2 light gates, using 1 light gate, using a motion sensor, and final one was using a ticker tape. In the previous chapter we learned that these methods can be used to measure the speed. Now we will learn the methods that can be used to measure acceleration. Okay, so we can use light gates like this. We can also use ticker tape, the ticker tape timer. So here are two methods, and then the other method is again using a motion sensor. Okay, so again light gates, ticker tape timer, and the motion sensor can be used also to find acceleration. Okay, determining velocity and acceleration in the lab, then measuring velocity and acceleration. Okay, we will see what this is. A micromechanical acceleration sensor is used to detect sudden accelerations and decelerations as a vehicle travels along the road. This electron microscope image shows the device magnified about 1000 times. Okay, so you know this is how the airbags work. The airbag is connected to these accelerometers. You call these accelerometers. Okay, you might have them in your phone also. Okay, your phone can also have that accelerometer. Then in a car crash, the occupants of the car may undergo a very rapid deceleration. This can cause them serious injury, but can be avoided if an airbag is inflated within a fraction of a second. Figure 2.7 shows the tiny accelerometer at the heart of the system, which detects large accelerations and decelerations. The acceleration sensor consists of two rows of interlocking teeth. See that in the picture here, and this is zoomed several times, or in other words you can say this is the image formed using a microscope. In the event of a crash, these move relative to one another, and this generates a voltage which triggers the release of the airbag. Very easy to understand. At the top of the photograph you can see a second sensor which detects sideways accelerations. Okay. This is important in the case of a side impact. The sensors can also be used to detect when a car skewers or skids, perhaps on an icy road. In this case, they activate the car's stability control systems. Okay, now we'll learn how to measure acceleration in the lab. Okay, so what we have here is one light gate, and you can see this card is cut into this shape. Now what happens is when the trolley passes through this light gate, in the beginning when this part of the card passes through, it blocks the light, and then over here, so imagine now this is going through this. Okay, so it's only this part and this part of the card that blocks the light. No part of the trolley blocks the light, only the part of the trolley above the part of the card above the trolley. So what happens here is, in the beginning, so when this passes through this blocks the light, and over here it unblocks the light. Again it blocks the light, and then over here again it unblocks the light. Okay, so we have this connected to a timer. Then we can time how long it took for this length of card L1 to pass through like this. So this L1 divided by T2 minus T1 will give you the initial velocity. Okay, because velocity is changing displacement over time. So the displacement is L1 and the time is T2 minus T1. Okay, then over here also we find it the same way. We can find the speed over here, that is the final velocity. So we know initial velocity, we know final velocity, and one more thing is the time. Now we will see over here. See, now we know how to find the V, we know how to find the U, and the time taken is T3 minus T1. Okay, so here because that is the time for the change in the velocity, V minus U. Okay, so this is what I explained. U is equal to the initial velocity is the length of the card L1 divided by T2 minus T1, and over here V is L2 divided by T4 minus T3. and acceleration is v minus u over t3 minus t1. And don't confuse it. Sometimes students might think t4 minus t1 or t4 minus t2. Remember, it's t3 minus t1. Okay, so that is one method, using a light gate and the interrupting section of the card. The second method is using a ticker tape timer. So we have ticker tape, and you know the time between dots is 0.02 seconds, because the ticker tape machine makes 50 dots in 1 second. So 1 divided by 50 is 0.02. That is the time between dots. Okay, so you can see over here, every 0.02 seconds there is a dot, and the distance between the dots is increasing, which means the object is accelerating. Now the dots are printed at a constant rate, but if you pull it out from that machine faster, then the distance between gaps increases, which means the object is accelerating. Okay, each section represents 0.10 seconds. So if you cut it every 5 dots, 1, 2, 3, 4. So here, if you count it, 1, 2, 3, every 4 dots. Okay, so from here to here it's 0.02, 1, 2, 3, 4. So 5, right? It should be 5. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so 0.02. Yeah, it should be every 5 dots. So if you cut it every 5 dots, then the distance between adjacent dots is 0.02. So if you cut it every 5 dots, then it's 0.02 into 5, which is 0.10. Okay, so the time for each length of card, then if you cut it every 5 dots, will be 0.10 seconds. And if you place it side by side like this, you can get a velocity time graph. By placing the sections of tape side by side, so you cut each every 5 dots and place it side by side, then here you will have your y-axis, here you will have your x-axis, then you get a velocity versus time graph. By placing the sections of tape side by side, you can picture the velocity time graph. The length of each section gives the trolley's displacement in 0.10 seconds, from which the average velocity during the this time can be found. Okay, so again, the length of each section gives the trolley's displacement every 0.10 seconds, because this okay, so here 1, 2, it's only showing 4, there should be 5. Okay, 2, 3, 1, 2, 3, 4. Yeah, so if you cut it every 0.10 seconds, then that is this length is the distance traveled by the trolley every 0.10 seconds. Okay, so that's why here this axis will be displacement, the y-axis, this axis is the time then. Okay, so by placing the sections of tape side by side, you can picture the velocity time graph. The length of each section gives the trolley's displacement in 0.10 seconds, from which the average velocity during this time can be found. This can be repeated from each section of the tape, and a velocity time graph drawn. The gradient of this graph is equal to the acceleration. You know, the gradient of velocity time graph is the acceleration. Okay, sorry, this is not displacement. By placing the sections of tape side by side, you can you can picture, you can picture the velocity time graph, because here this is the displacement, and the time intervals are the same, every 0.1 seconds. So here to here 0.1, here to here 0.1. Yes, so then you are getting a displacement time graph, y-axis displacement, x-axis time. But what they are saying is, from that you can interpret the velocity time graph also. Okay, so once you get the velocity time graph, you can get the acceleration time graph. Alright, so that's what we have over here. First section of tape 0.0, the second section of tape 0.10, So you see the time intervals are 0.10. Over here you can see that. And now you can plot a velocity time graph. See, deducing, and once you have the velocity time graph, you can draw the acceleration time. You can get the acceleration time graph, because gradient of velocity time graph is acceleration, deducing acceleration from measurements of a ticker tape. Okay, so you can see it's a line, straight line. That means the acceleration is constant. Okay, let's see how they drew this graph. Now using this, you can see the displacement is this is the section of tape, time interval, then length of section 2.3. then what happens, so in the beginning, first section of tape, that is this one, is 2.3, second section 7.0, third section 11.6. you see the displacement is increasing for a certain time interval. Okay, then what we can do is use your calculator, divide 2.3 by 0.1, you will get 0.23. divide 7 by 0.1. Okay, so the velocity is displacement divided by time, 2.3 divided by 0.1, that will give us 23 centimeters per second. Now we have converted it to meters per second here. When you convert from centimeters per second to meters per second, you can divide by 100. That will give us 0.23. Same thing over here, 7 divided by 0.1, that will give us the speed in centimeters per second. You can convert it to meters per second. 70 centimeters per second is 0.70 meters per second. So look at the unit over here. Here it's meters per second, here it's centimeters, here the time is in seconds. Okay, once you do that, you can plot the points. So 0 and 1.1. So 0, this is velocity, yes, sorry. So the 0.23. Okay, so there. Then again, when the time interval is 0.1, okay, 0.1, then it is this value, which is 0.7 something. Okay, so over here it's 0.70. then when it is 2, it will be 1.16, so somewhere there 1.16. then what you do is find the gradient of this, that will give you the acceleration. You can see that it's a straight line, that means the acceleration is constant. This is how you do it using ticker tape. And the last method is using the motion sensor. The computer software which handles the data provided by the motion sensor can calculate the acceleration of a trolley. However, because it deduces velocity from measurements of position and then calculates the acceleration from values of velocity, its precision is relatively poor. Okay, and remember, the motion sensor should be kept in the direction of motion of the object. It should be parallel and in front or behind the object that is moving, because it sends waves. Okay, it sends the waves and it detects the reflected waves, and that's how it gives you the displacement time, velocity time, or acceleration time graph. We connect it to a computer and then you can get the graphs. But the problem here is, because it deduces velocity from measurements of position and then calculates acceleration, the precision is poor. Okay, so there are more questions. Now this is questions 6, 7, 8. These are questions 6, 7, 8. Make sure you do all these questions from 1 all the way to whatever the last question is in this chapter. These questions here are based on what you learnt just now. You can see here the card is there, and to do this question, I think you need to use this formula. Okay, so make sure you understand it is T3 minus T1. Okay, T3 minus T1. Okay, so you can do these questions. Then we have the equations of motion. These are also called the SUVAT equations. SUVAT. Okay, we are using the symbols over here. SUVAT. SUVAT equations, also called the equations of motion with constant acceleration. S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration, T is the time. And you have to know all these equations. You should be able to use them. Okay, see the meanings of the quantities or symbols are also given here. Take care using these equations. They can only be used for motion in straight line, because if the direction is changing, if it's not moving in a straight line, the direction is changing, so that changes the velocity even if the speed is constant, because velocity is a vector quantity. If velocity is changing, there is acceleration, because acceleration is changing velocity over time. Okay, then okay, the next page has some examples. Like I mentioned before, it is very important that you understand how to use these equations. So you have to memorize these equations, and you should be able to use these equations to do questions. And it's very easy if you understand the steps. Whenever you get a question, you write down the quantities that are given and the quantity that you need to find, quantity or quantities that you need to find. Then figure out which equation has all those quantities, including the quantity that you need to find. Let's do this example. It's very important that you do go through a lot of examples and do a lot of questions on these equations. The rocket shown in figure 2.12 lifts off from rest with an acceleration of 20 meters per second squared. Initial velocity is 0, because they say lifts off from rest. So U is 0. You can see they have written it down over here. With an acceleration of 20. Acceleration is 20 meters. Calculate its velocity after 50 seconds. So you have to find V after a time of 50 seconds. So T is 50, V is what you need to find. So which equation out of these 4 equations has all those 4 quantities? V, U, A and T, that is the first equation. So this is how we know which equation we are supposed to use. That's why we write down the quantities like this with the unknown quantity, and then we see which equation out of those 4 we have to use. So that is this equation. V is equal to U plus AT. U is 0 because they say starts from rest, and A is given. After a certain time T, we are supposed to find the velocity. So that means we are supposed to find the final velocity. We get 1000 meters per second. So the rocket will be traveling at 1000 meters per second after 50 seconds. This makes sense since its velocity increases by 20 meters per second every second for 50 seconds. This acceleration units are 20 meters per second squared. That means every second, after every 1 second, the velocity increases by 20 meters per second. So after the first second, the velocity is 20 meters per second. After the second second, the speed is 40 meters per second. So every second, the velocity is increasing by 20 meters per second. That's what we mean by an acceleration of 20 meters per second squared. 20 meters per second squared is 20 meters per second per second. You could use the same equation to work out how long the rocket would take to reach a velocity of 2000 meters per second, or the acceleration it must have to reach a speed of 1000 meters per second in 40 seconds, and so on. Using this equation, if you want to find the velocity after, let's say, 40 seconds, you substitute 40 for T. Acceleration is constant, so then you can get the velocity after 40 seconds. Here we found the velocity after 50 seconds. Similarly, if you want to find the time when the velocity will be 2000 meters per second, you can substitute 2000 meters per second for V. You know what U is, A also you know, then you can find the T. The time taken to reach that velocity of 2000 meters per second, or whatever velocity you want to find, if you want to find how long it took to reach that velocity. Okay, so that is that example. Let's go through another example. You see, this is what I mentioned earlier about the card. Over here you can see this equation, T3 minus T1. So if you start at this end, you have to end also at the same end like this. Similarly, over here, if you look at this car, the timing starts at this point. So the timing should end also at the same point on the car. If you start at the start timing from the front, you have to end also at the front. The car shown in figure 2.13 is traveling along a straight road at 8 meters per second. It accelerates at 1 meters per second squared for a distance of 18 meters. How fast is it then traveling? So you have to find the final velocity. Like I mentioned previously, it's better if you can draw a diagram and list down the quantities. You can also label the quantities in the diagram. Instead of writing it down like this on a side, you can label all the quantities given in the question in the diagram with the unknown quantity. It becomes a lot more clearer that way. Okay, so initial velocity is 8, acceleration is 1 meter per second square. So here it's not labeled, but you can label it. Acceleration is 1 meter per second squared, and the distance is 18 meters. You are supposed to find the final velocity. So which equation has those two? So here also you can write A equals 1.0 meters per second square. So you have to see which equation has U, A, V and S. U, A, V and S. Okay, U, A, V and S. So let's see which equation has all those four quantities. U, A, V and S. That is this equation. U, A, V and S. So we are supposed to use this equation because it has all the quantities, including the quantity we need to find. Okay, so you can write down the quantities and you're supposed to, and that is this equation. Now very easy, substitute into this equation, then you will get the answer. U is 8, A is 1, you can see that over here, 2A, S is 18. Then simplify. Remember to take the square root. Sometimes students forget to take the square root. Okay, so V squared is equal to 100 and you are supposed to find V. When you take square root, that is equal to 10. So the car will be traveling at 10 meters per second when it stops accelerating. If you want, you can use the units of quantities so that it's clear to you what the unit will be at the end, but you can also do it without substituting the quantities. If you substitute all the quantities units in SI units, your answer will also be in SI units, and that's what they are indicating over here. See, if you don't use the units, then however including the units can help to ensure that you end up with the correct units for the final answer. Next example, a train traveling at 20 meters per second accelerates at 0.50 meters per second squared for 30 seconds. Calculate the distance traveled by the train in this time. Okay, so initial velocity is 20, accelerates at 0.5 meters per second squared. The acceleration is 0.50 meters per second squared. We can write all the quantities, and the time for that acceleration is 30. And we are supposed to find the distance traveled by the train in this time. So that means S. Now I mentioned earlier, if a train is traveling in a straight line, it's moving in one dimension. So the displacement is increasing and we measure it from a certain point over here. It's a starting point of the train. Now you have to see which equation has all these four quantities, and that is this equation. S is equal to ut plus half at squared. Okay, it's better if you have all the equations written down, so for each question you can see which equation you are supposed to use. So we have this equation. U is 20, T is 30, half A is 0.5, and again T is 30. Remember to square the T again. Like I said, students forget to square. Then we will get 825 meters. So the train will travel 825 meters while it is accelerating for a time of 30 seconds. So after 30 seconds, this train has traveled 825 meters. Okay, more examples. Example number 7. The cyclist in figure 2.15 is traveling at 15 meters per second. She brakes so that she doesn't collide with the wall. Calculate the magnitude of her deceleration. Initial velocity is 15, final velocity over here should be 0. They are asking the deceleration, so we need to find what the acceleration is. It will be negative, and then we can write the answer as a positive value, which is the deceleration. So you know v will be 0, just before she hits, she stops, let's say. So you can label all of that. U is 15, v is 0, the distance traveled or the displacement is 80. Now if it's a distance traveled in a straight line without coming back, then the distance and the displacement are the same. So she's moving in a straight line and she's not coming back. So that's why the displacement and the distance are the same in this case. Okay. I told you in the previous lesson, the distance depends on the path. The distance depends on the shortest, the displacement depends on the shortest distance between the starting point and the ending point. So over here you can see this is the starting point, so just before it hits the wall is the ending point, and the path is a straight line. So that's why the distance and the displacement are the same in this example. Okay, you know u, you know v, you know s, you are supposed to find a. So the equation that has all those quantities u, v, s and a is this equation. So we use this equation, we are supposed to find a, therefore we can make a the subject of the equation. Now if it is difficult for you to make this the subject of the equation, you can first substitute the numbers and then simplify and then get the value of a. Okay, so this is easy, but there may be some other questions where if you try to make a certain letter the subject of the equation, it's very complicated. So in that case you can directly substitute, simplify and then get the value. Alright, so final velocity is 0, initial velocity is 15, and then 2 times s is 18. We will get a negative value for acceleration. That means it's a deceleration. You can clearly see she's slowing down. So, but deceleration we give it as a positive value. So the deceleration is plus 6.3 meters per second squared. So the cyclist will have to brake hard to achieve a deceleration of magnitude 6.3 meters per second squared. The minus sign shows that her acceleration is negative. That is a that means it's a deceleration. Okay, so please answer all these questions. It's very important that you answer all these questions. And the next topic is about the derivation of those 4 equations. Okay, so let's say we have a graph like this. An object starts with initial velocity u, and after a time t, the velocity is v. You have learned that the gradient of this line gives you the acceleration, and the area under this is the distance or displacement. Okay, this is the displacement, and in this case if it's not coming back, the distance and the displacement are the same because it has to be moving in a straight line. Alright, then the gradient of a velocity time graph is the acceleration, and that's what you see over here. Acceleration is v minus u over t, and acceleration is the gradient. And you can also see here this is v minus u, this is v minus u, and then if you do v minus u over t, that will give you the acceleration. So that's how they get this equation over here. Then about the area, the displacement s is equal to ut plus half at square. After time t, the displacement is this area plus this area. So this area is the area of a rectangle, that is u times t, ut, and this area here is the area of a triangle, that is half into base into height. Okay, so half into base is t into the height is v minus u, and v minus u is at. So what you can see here is half into base is t and the height is at. So it will be half into t into at, which is half at square. Okay, so that's how they substitute for v minus u, this length v minus u, say they have substitute at, and that's how you get this one. Okay, so the first equation, I already explained how to get that equation. It is the gradient of the graph, and if you rearrange, you will get v equals u plus at. This is the first equation, equation number 1. in the out of those 4 equations that you saw. This is the first one. Then let's see how to get the second equation. We already know that, okay, let's go into this directly. So the displacement is the average velocity times the time. Displacement is velocity times time, and this is the average velocity. How you find the average velocity? Now again, the displacement is area of this this part, this area below the line, and the area below the line can be found like this. Now this is a irregular shape, right? So what we can say is, if we draw a line like this, this area over here is equal to this area over here. Okay, otherwise we will have to find this area plus this area plus this area. So we'll have to find the area of a rectangle, area of a trapezium, and again we'll have to find the area of a triangle. So it's too much work to do. What we can do is, if you draw a line like this, you can see that this area here is equal to this area here. This triangle is identical to this triangle over here. So what we can say is, now if once we draw a horizontal line, so what we'll do is we will draw a horizontal line such that this area and this area is the same. Then very simple, it's this length over here into this length over here that will give you the displacement in time t. Okay, so we can use this equation. S is equal to u plus v divided by 2. That will be the average velocity. Now if you take this number and if you take the number here, if you get the average of those two, that will be the number in the middle. Okay, so that will be the this length, which is u plus v divided by 2 times the time t, which will give you the area of this big rectangle, which is equal to the area under the line, which is equal to this area plus this area plus this, because this area is equal to this area. Okay, so that's how you get the second equation. S is equal to half u plus v times t. Okay, or we can say S is equal to u plus v divided by 2 times t. This is the average velocity. We can use this again only when the acceleration is constant, because if the acceleration is constant, you can't do this to get the average velocity. Only when the acceleration is constant, when it's a straight line only, you can use this equation to get the average velocity. That's how you get the second equation. Then the third equation you can get by substitution. From equations 1 and 2, we can derive equation 3. The first equation was this, the second equation was this. Substitute this in over here. So v is equal to u plus at. Substitute for v, u plus at. Then what you will get is 2u plus at times t divided by 2. So 2u, and you are multiplying by what is outside over here, 2u times t, 2ut. Then over here this term at squared. Okay, then numerator is the same, so we can write it like this. So this will give us this 2 and this 2 cancels, so we get ut plus half at squared, which is the third equation. You see here, ut plus half at squared. And the final one is this one. Now there are some mistakes over here which you have to rectify. I will tell you what those mistakes are. Equation 4 is also derived from equations 1 and 2. We had equation 1 and equation 2. Now remember, in the equation 2, it's u plus v, not u plus u. See, it's u plus v. Equation 2 is u plus v. So you can change this to a v if it is the same in your textbook, u plus v. Okay, then what we do is substitute for time from equation 1. So for time we substitute in equation 1, from equation 1 into 2. So what we do is we make t the subject of this equation. That will be v minus u over a. T from the first equation, if you make t subject of the equation, t is equal to v minus u over a. So substitute that in here. That's why here also there is a mistake. It should be v minus u. So change this to a minus sign, and here it should be multiplication, so change this to a multiplication sign. Here it should be a multiplication sign, here it should be a minus sign. Now this part is u plus v, here it should be u plus v, here it should be a v. So we are using this equation, substituting for t into this equation from this one. Here it should be u plus v over 2, here it should be a v, then here it should be a multiplication sign. When you make t the subject of the equation, here you get v minus u over a, v minus u over a, so it should be a minus sign here, it should be multiplication here. Then what you can do is you can simplify further, you can multiply the whole equation by 2a. When you multiply by 2a, you get 2as, and then here it's, I told you it's supposed to be multiplication, and 2a cancels, you get v u plus v, okay, u plus v times u minus v. Here it should be a minus sign, here it should be multiplication. So then this is okay, this is correctly done. Here there are printing mistakes, here it should be v, here it should be multiplication, here it should be a minus sign. Then finally you get v squared minus u squared, and that's how you get this equation. So 2as equals v squared minus u squared. If you rearrange, if you make v squared the subject of the equation, you get v squared is equal to u squared plus 2as. This is how you derive the 4 equations of motion for uniform acceleration. They are also called the Sweat equations. Alright, then there are more questions. Using these equations, we can find out, the police can find out whether a person actually stopped, or whether a person is guilty of an accident. Okay, and there are questions like that over here. The police frequently have to investigate road traffic accidents. They make use of aspects of physics, including the equations of motion. The next 2 questions will help you to apply what you have learned to situations where police investigators have used evidence from skid marks on the road. Now the skid marks appears once the brakes are applied and the wheels are locked. You will see the black marks from the tires on the road, those are skid marks. Okay, so you can try to answer these questions. When you do these questions, you will understand it. The next topic is uniform and non-uniform acceleration. We can also use the word constant and non-constant, or steady and non-steady. Here constant acceleration and changing acceleration. So you have to be familiar with the different words, because in past papers they can use these different words: steady, uniform, constant, not changing, same, all mean the same thing. Alright, here we have a situation where the acceleration is changing. Now those 4 equations can be used only when the acceleration is constant. Here is a velocity versus time graph. First thing you have to do when you see a graph like this is look at what the axes are. You can see the gradient is decreasing with time. That means the acceleration is decreasing with time. The curved velocity time graph cannot to be analyzed using the equations of motion, because the acceleration is changing. Okay, so we can see how to find the gradient at a particular point on this graph. Now not only in this, in any graph, the way you find the gradient of a curve at any point is by drawing the tangent to the curve at that point. Or else, if you know the equation of the graph, those students who are doing mathematics will know, you can use differentiation and find the gradient at a particular point on the curve. Okay, so here you can see what we do is we draw a tangent and we find the gradient of the tangent. And when you're finding the gradient of the tangent, make sure when you draw the tangent, it should just touch the line. And when you're drawing the triangle, make sure you draw a very large triangle, which is right angles, and use it to find the gradient. That will give us the acceleration. And to find the displacement, you have to find the area under the curve. That means you can count the number of squares under the curve and multiply it by the area of one square. That will give you the displacement. Or else what you can do is, like what we learned previously, you can draw a line like this, a horizontal line, Alright, so let's say you want to find the displacement in the first 45 seconds. So from here to here the time is 45. So what you do is, now it's a curve, you can't take the time to count all this, right? It will be very time consuming. So what you can do is you draw a horizontal line like that, so that the area over here is equal to the area over here. The area that is above the line between the curve, below the curve, is equal to the area below the line to the left of the curve. So if, let's say, you draw a line where it says 20 meters per second, if you draw a horizontal line over here, then the area above that line is equal to the area here, which is to the left of this curve and to the right of the y-axis. If this area and this area are equal, then what you get is, you get a regular shape, which is a rectangle. Can you see that? So what you do is find the area of the rectangle. So this length times this length will give you the area of the area under the curve. Okay, so that's the fastest way to do it, and that is also an estimation or approximation, but it is much faster. Okay, so remember those two. There are questions actually in the past papers that I've seen where they asked you what is the area under this, and they have labeled it. So this area, and the most common thing that students will think it's area under this, right? Like this area, but there was no answer for that. In that MCQ paper you have 4 options, right? This area plus this, whatever the areas that were under this, that was not given, but there was an area that was equal, like this area is equal to that, and they have given this plus this plus this. So that means you have to find the area of that rectangle which was labeled and then do it. Okay? So when you do past paper questions, you will understand this better. Over here they are explaining another method. The area of the triangle. Now what you do is, this is, now counting is tedious to count, but you can save yourself a lot of time by drawing a line from the origin to the point at 20 seconds. From origin to over here. That is if you want to find the displacement in the first 20 seconds. But what I mentioned is the best way. Okay, the area of the triangle is easy to find, 200 small squares, and then you have to count the number of small squares between the line you have drawn and the curve on the graph, about 50 squares. So what you do is you draw a line from here to here, then you find the area of the triangle, and then count the area between the curve and the line. Add the two together, then you will get the answer. Okay, so that is another way, but the way I told you is the best way. Okay, the fastest way. Okay, so here is what they are explaining. In each case, this one square is this much square, and then you will get the displacement. Okay, so make sure you answer all these questions and check the solutions in the drive or in the CD. The next topic is acceleration caused by gravity.